So this is word problems, okay? Everything changes. A is often referred to as the initial, A is the initial amount present. Like how much do you have at the very beginning? It could be bacteria, it could be population, it could be amount you've invested, you name it, okay? So that's A, right? B is asking you what's happening to the initial amount. Is it going up or is it going down? Obviously, this is a recap. B is greater than 1. It means you're increasing. B is less than 1. You're decreasing. X will often be time. So that could be in days, months, years, you name it. It could be hours. It could be seconds. You have to just read carefully. So there's your 3 components that we're going to consider when it comes to a word problem. A and B are going to be numbers. X is going to be obviously a variable, and what the units are is going to be given to you by the question. Okay? So let's do a few hypotheticals here. You should always ask, is the population increasing or decreasing? Is the investment increasing or decreasing? To determine B, read the question. It will be less than or greater than 1, of course. So example 1. Let's just do example 1 here. If the question mentions a decrease of 5%, the equation would be, okay, here you have to be careful. It's a decrease of 5%. Okay? That means that you have 100% would be the total, but you're decreasing 5% every year, which means that you have 95% left every single year. So this right here, we're going to write down, this is the decrease. What's happening to the initial amount? It's decreasing by 5%. Therefore, we take 100 and we subtract 5%. So we are technically 95% left every time. So therefore, example, y would be a 0.95 to the power of x. So when you look at this, you should realize, wait a minute, 0.95, that means that we're losing 5% every year. That's what's happening here. And this is how you do it. Don't put the 5 in here. You always go with your starting point. You start with 100, you subtract 5%. You're losing 5% every year. So you're left with 95%. That's what goes in here. Okay, so B is equal to 0.95. Let's write that down under, and that's what goes in here. And remember, is this less than 1? Is this between 0 and 1? Yes. So this will be a decreasing function, right? You're losing. Okay, there we go. If the question, so example 2, if the question mentions an increase of 5%, okay, so I'm going to go orange again here. The equation would be, well, let's see here. We start with 100%. That's our like initial population. We're going to go up by 5% every year. So what do we end up with in this case? It's 105% left, but you wouldn't say left, right? Increased to 105%. So what would B be in this case? You divide that by 100, what do you get? 1.05. So my resulting equation, we don't know what A is just yet, but we do know that what goes in the brackets, which is the variable B, would have to be 1.05. So here you observe a 5% increase per, let's say it's per year. Here you observe a 5% decrease per year. So you're always wondering, what's happening from 100%? Are you going down or up from it? Okay. So here are some examples where we do know A. In each of this scenario, write your equation. You invest $6,500. That is A. That's your initial amount. Your investment earns 2.5% annually per year, that is. So what is B in this case? Some students might just be tempted to say, oh, that's B, 2.5%. That's not correct. It's 100 plus, if you're earning, what's happening to your money? Is it growing or decreasing? It's going up, right? Yeah. So you go plus 2.5, so it's 102.5%. So B is 1.025. So let's write it. We know what A is. We know what B is. We can now write our equation. Y is equal to $6,500 times 1.025 to the power of X. There we go. Can you give this a try? Try to write your equations based on those the write-ups. All right. Small town has a population of C's. I think that. Let's just get rid of that. 578 people. I bet. It has a decrease of 12.5%, its population size each year. So let's figure out B. We have a decrease happening here, so we're going to subtract the 12.5, and it's percent, right? We end up with 87. I can do this. 87.5%. But we do not want B as a percentage, so we turn that into a decimal. Okay, so that would be B. So I can say that it's 578 to start, and that population is decreasing every year. So this could tell you how many people would be left in 10 years from now, 15 years from now, 20 years from now, right? We could actually use this to figure that out. The number of bacteria in a petri dish is 25,000. It triples every hour. What's up with that? It triples every hour. In this case, B is simply 300%. Because, right, when you have 100% and you triple it, it's 300% that you have left, right? That is after. So B is simply 3. So you would go Y is equal to 25,000, and then it's 3 to the power of X. Just think about it. After 1 hour, what's 3 to the power of 1? That's 3, right? So 3 times 25,000, you'd have 75,000. So you tripled your bacteria after just 1 hour, okay? So that is that. Okay, so now you kind of understand how to put them together if you must, if you have to. Also go the other way. If they give you the equation, you should be able to deduct. Okay, deduct what the percent increase or decrease is. And I just skim by this. I want to make sure you understand that. I'm going back to 7 real quick. What I mean here is I need you to be able to look at this and be like, oh yeah, this is exponential. And if I ask you what's happening here, I should be able to get you to look at that value and be like, oh, there's a 5% decrease every hour, every year, we don't know that. They'd have to give us more information. But just by looking at it, you're like, yeah, 5% drop. If you look at this one, you should be able to see, oh, there's a 5% increase every hour or every day, whatever X ends up being, okay? So I need you to be able to deduct that, Okay? All right. Let's go over here. Euler's number is denoted by the letter E. You're going to see E a lot. And it's used in many areas involving growth or decay. It's a very important constant found in many contexts. Okay? An irrational number, Euler's number is 2.71828, and it never stops. It's like pi. It never stops. It's a forever series. Okay? It's used in everything, in exponential growth and radioactive decay. It's also used in finance to calculate the wealth, how much your wealth can grow due to compound interest. But don't confuse Euler's number with Euler's constant, which is 0.57721. The good news is you don't need to remember any of this. I'm just like giving you a little intro. Like, what's E, Mr. Dirksen? This is why we use E. And grab your calculators. I'll show you where E is located. Okay, so can you see my calculator on there? All right. The first location of E is above the division button. So you see the division button, you see that E there? So if you go second division, you call up E, you hit enter, it will tell you what the first couple of digits are of E. But this is not the one that I want to use most often. Let me just try something here. There we go. You see the one that's E to the X? It's right next to 4. There's that LN button. There's that LN button. You see the E to the X right there? That's the one we're going to use most often. So press second, and then natural log. That's what LN is. You don't need to know about it just yet. But then you can put a variable up top. So let's say you wanted to put X in there. Press X. You could actually use E that way. Okay, so that's where E is located. This is the one that we use most often. But just so you know, it's there. We have a button for E. Okay? Therefore, you may see an exponential equation that looks like this. Y is equal to 5e to the x. And that's not a typo. E is a number for us. Okay? So we press second ln to access E. Okay? That's what we press there. By the way, what do you think it's going to be? Is it going to be increasing or decreasing if E is in there? It's 2.71. It's bigger than 1. It's always going to increase. So it's always population growth for the most part. And so that's that. Now, this box right here is extremely important. This is used for regressions. Write that down. This is a system that we use to perform regressions, to come up with points. Doubling, there's something called doubling period. I'm going to highlight doubling period and half-life. When you have doubling periods, you're having an increasing situation. Okay? And what is doubling period, guys? Is the amount of time for money or population to double. And it only applies to increasing functions. Here's your example. A population of 1,000 has a doubling time of 10 years. A population of 1,000 has a doubling time of 10 years. Determine the equation. Doubling time is exponential, guys. There's no question. Don't be trying to find a linear or quadratic or any of those. Doubling time is exponential. What you will do is this. You will go time and population. This could be time and money. It could be anything. It could be bacteria. You name it. What does 1,000 tell us? It tells us that at time 0, at the very beginning, we have 1,000 people, right? And what is the doubling time here? It's 10 years, correct? So every 10 years, the population doubles. That's what that means. Every 10 years, population doubles. It could be every 10 hours. It could be every 10 minutes. It could be every 15 minutes. It depends on the question. In this particular one, it's every 10 years. So after 10 years go by, from 0 to 10, what's our population going to be? 2,000, right? You doubled it. Doubles. What happened on the left side for our time? We went plus 10, right? You can't go 0 times 2. That's 0. So you have to add on the left side. Another 10 years go by. We are at 20, correct? What's my population now? 4,000, because you double what you had previously. That's technically all you need for your L1 and L2. So we go L1, L2, stat, calc, exponential regression. How do you know it's exponential? Because it's doubling time. Like there's no question about it. So let's try that. Write everything down, have it all set up. Let's enter this into our calculators. Stat, edit, 0, 10, 20. Can I tell you the most common mistake, the common error? Do you want to know the common error? Students start with 10. They go 10, 1,000. And then they go 20, 2,000. Like they skip the 0. But it's times 0, okay? We start with 0. That's if you know the initial population. So 1,000, 2,000, 4,000. Let's go stat, calculate. Let's go, you're going to have to dig for this one. You got to go way down to exponential regression. You don't see it at first. You got to go way down. Hit enter. We're going to go second 1, comma, second 2, comma, alpha trace. Type that in, and there's our equation. Wait a minute, what's that 1.07? What does that tell us? An increase of how much percent per year? 7% per year. So there's a doubling time. It just tells you how much it doubles. But if you wanted to know per year, you're increasing 7%. Increasing 7% per year. So if you wanted the yearly amount, there it is. You're going up by 7% per year. But it amounts to doubling your population every 10 years. Okay, how about half-life? Time it takes for the population to reduce to half its initial population. Half-life is also linked to decay or decrease. Things are going down, okay? So basically, example here. initial amount of bacteria is, let's go 5,000. No, I'm going to use a nice round number. Let's use 8,000. With a half-life of, let's say, 2 hours. Again, time and population, bacteria in this case. Let me just bring this up. So at the very beginning, at time 0, we have 8,000 bacteria present. 2 hours go by, right? You got to go plus 2 basically. You got to go plus, plus, plus. What happens to my population? You half it. Half-life. Half. So it's 4,000. I use that nice round number. It won't always be round. You have to do whatever you need to do. Decimals are fine. Another 2 hours go by. That'll get me to 4. You are halving it again. You're down to 2,000. That's all you need. Three points for this to work. We go L1, L2, stat, calc, exponential regression. Let's come up with our equation. I will type this in. 0 to 4. 8,000, 4,000, 2,000. I'm going to go, I already did the exponential regression, so I'm going to my home screen and I'm just running it again. Okay, so there it is. 8,000, 0.71 to the power of x. Okay? If I asked you, can you observe what the percent decrease is per, what are we in? Per what? What is x in? Hours, right? So what percent decrease per hour? 29%. You see that? I'm going to go 1 minus 0.71 here because it's a little harder to see if it's less than 1. So it's a 29% decrease per hour. Okay? Somebody wants to come in, eh? Hey. Oh, you done? Yeah, go ahead. 29% decrease per hour. That's the equivalent of what's happening here. Okay? All right. Let's continue. So this is how, this is the classic regression situation, doubling period or half-life. Okay, I think I'm going to let you struggle a little bit. I want you to answer all of these questions based on what you see there. I think you know enough. Maybe one little warning. Your window to see this thing. Look up here for word problems. We're in quadrant 1, right? So you're going to have one of two scenarios. You might have something that starts and goes up, or you might have something that is up and goes down. You're going to have this, okay? This is where b is greater than 1. This is where b is between 0 and 1. So No longer do we look at the whole thing, all four quadrants. By the way, this only happens in the top two, right? We never cross the x-axis. So you're gonna look at this scenario, okay? Type this in, see if you can make it show up. You have zoom fit, you have all those zooms to help you out, and go from there, okay? So much time left. So make sure you copy this down and you have one full example, okay, so you can refer to it. What's the initial population? Explain. You don't even need to graph this. You don't need to do anything if you just look at your equation, okay? Initial amount given by A, right? If you consider this form, so I'm being very specific here. I'm saying, hey, if this is the form, then A will tell me the initial amount. Therefore, initial population is 1,500 bees. Okay, that's it. That's all you need to do there. Is the population increasing or decreasing? It's increasing. Since B is greater than 1, the population is expected to increase. Something like that, okay? That's all. That's all I need to do there. What is the rate of increase or decrease? It's an increase, we've determined that. Stated as a percentage. We go 1.15 minus 1, that's 0.15. Just in the bin. If you multiply that by 100, you get 15%, but you need to be a bit more specific. Per what? What is x? What is my variable x in this case? It says time in years, okay? So it says 15% per year. So just look back at your question, because time is in years, therefore that increase is per year. And this is new here. How long will it take for the bee population to double? Doubling time, okay? Let Y2 be 2 times whatever A is, whatever you started with. So that's 2 times 1,500, which is 3,000. You're going to figure out how long does it take me to go from 1,500 to 3,000. Then we're going to go second, trace, intersect. Okay. Second, trace, intersect. So I'm going to grab my calculator, and this is where I need to make it appear. I'm going to pretend like I don't know what's happening. What's happening to this graph? I know it's increasing because B is bigger than 1. I'm going to try zoom fit. Zoom fit does a pretty good job. Maybe I can just use it as is. I would like to make sure you understand that Y min should be a little bit into the negative still. I'm going to try this again. So I'm going to let Y2, basically you can see it right here. Whatever A is, you double it. So it's going to be 3,000 equals. So this is the 3,000 mark for population. So I'm going to figure out what time that happens. Second, trace 5. Just go a little closer to it. Enter, enter, enter. And there it is. It's 4.96. 3,000 is that intersection. It takes, or doubling time, it takes 4.96 what? What is time in here? Years. To double. This is my doubling time. I'm going to highlight that. That's my doubling time. Every 4.96 years, your population is going to double, guys. Every 4.96 years. So guess what? If I wanted to know when are we going to have 6,000 bees, that's double, right? It would take another 4.96 years to get there, right? So once you determine the doubling time once, it stays the same. It's 4.96 years. That is the doubling time. Okay. How long will it take for the population to reach 9,250 bees? Remember, we want time when we have this many bees. That's basically what they're saying. So again, we have to go y2 is equal to 9,250. Second, trace, intersect. And let's go ahead and do that. Will this fit into my window? I'm not sure. I should have checked my Y max right away. Okay, I'm not seeing it, so I'm going to check my window. My Y max is 6,000 only. So I'm going to go, 10,000. Make sure that I can see it. Okay, so now I'm looking at all the way up to 10,000. There's the 9,250 line. I need to keep chasing my curve a little bit. So I'm going to go window, X max. I'm going to go 30 maybe. Try that again. There it is. I can actually see the intersection. So second, trace 5, enter, enter, enter. That is 13.02, 9250. So 13.02 years for that to happen. This is not a doubling time. This is just how long does it take from time 0 to this point, like how many years? There we go. How many bees after 60 months? Can I use months here? Units, I can't, right? Convert. So watch out when that happens. 60 months divided by 12 is 5 years. Okay, I have to have it in years. So it's basically asking you when time is 5, what's my population? What am I going to use for this one? Second, trace, value, x is equal to 5. Second, trace, value, x is equal to 5. That's 12,205.59. Can I leave it like that? It's population. You cannot. You have to round. Okay? Round. That's 12,205 or 6. It's up to you. But just make sure you don't leave it as a decimal. Yeah. Oh. I put in 15. Sorry, guys. Sorry. Stop rushing. Okay, 3,000. My bad. That's why we make erasers. Just when we thought it couldn't get any worse, right? It just goes down the drain. That's okay. Just give me a thumbs down. That's all good. That'll make up for it. 3,017. Thank you, Marty. Are you still hanging in there? It's fun stuff, yeah, I know. If the maximum capacity, you can't have more than that, is 15,000 bees. Determine the domain and range. So they're putting a cap on this thing. Let's do our sketch before we do our domain and range. This is time. This is bees. We go from here, and it just exponentially grows, but we will stop it, like we can't accept more growth after a certain point because of this sentence. So what is that max here? Is 15,000. What's my initial amount here? Like how much did I start with? 1500. So for my range, I have to stay between 1500 and 15,000. Does that make sense? Range is 1500 to 15,000. That's the easiest one in my opinion right now. But what about the domain? Time 0, right? I start at the very beginning when I keep tracking the bees. But I need to know this here. I need to know when do I stop? When is the time no longer counting because I reached the maximum? We have to find that intersection. So you let y2 equal 15,000. And then we go second, trace, intersect. I'll just give you the number right now. You have to make sure your window works. 1648, 15,000. Let me bring that up for folks that are back there looking over people's shoulders. Can I use 16.48? I absolutely can, because time is continuous. I can't figure out a portion of a year. I can bring it down to the days, to the hours even. So it's possible to do that. So that's my domain, and that is my range because of this. And you couldn't just be done with this without a nice graph, right? So we're going to do the graph on page 10. So we're going to do the usual time in hours. No, it's in years, sorry. Time in years. Then we've got population. I will just say number of bees. Okay, that's good enough. For time, I'm looking at my domain range. I need to go all the way to 16 something. So let's try here. 5, 10, 15, 20. That's, yeah, I'm just going to leave it like that. I could have probably done better than that, but I'm just going to leave it like that. That's consistent. And I need to go all the way up to 15,000. So I'm going to go 5, 10, 15,000. So 5,000, 10,000, 15,000, and you can do a 20,000 if you like. Basically, the way this one goes is I would start with my starting, like it's 1,500, so it should be right on the y-intercept. Y-intercepts are okay. Will there ever be x-intercepts for exponentials? Because it's right on the asymptote, right? Can't have that. 16, so this is 15, 16, 17, so it's somewhere in here. I'm going to go all the way up to 15,000, put a mark right there. And technically, if you just connect them, but make sure you have a bit of a curve, you are fine. I'm going to help myself with some of the points I've already figured out. For example, the doubling time happened at 5, almost 5, 3,000. So I'm going to put that point down there to help me out. And just make sure it has a curve. There we go. No arrowheads on this one. If it wasn't for that statement in G, you could have made an arrowhead to say it's going to continuously grow, okay? But it stops there. I'm just going to add, if no limit mentioned, then the domain would have been as follows. It would have been 0 to infinity, and my range would have been from 1,500 to infinity. Okay, so this is just, I'm gonna highlight this. This would have been a scenario where you actually put an arrowhead at the end of that curve. And let's make sure this is like you clearly understand that this is an aside. If no limit had been mentioned, then you go to infinity. So I'm going to take it easy on you. I'm just going to give you 2 questions to try. 12 and 13. I'm not doing any doubling time. Notice that I'm only giving you 2 questions, okay? So you can't say I'm like loading you up with homework every day. Just in the bit.